Hello everyone, I am Chen Xun. When working on LLC converters, many people have stumbled over dead time. If the dead time is set too small, the half-bridge node voltage has not yet dropped all the way down before the drive signal arrives, causing hard switching. If the dead time is set too large, the body diode voltage drop is high and loss is sore. So many students hold up this LLC development board and ask me how to calculate the dead time. We calculated the dead time following the COSS in the datasheet, so why does the measured waveform look so strange? The reason is simple. If you have not found the key to the problem, you cannot solve the key problem. The key is COTR. Let us review the modal analysis of the VDS charge and discharge phase to see what relationship COTR has with dead time. Look at this circuit. The moment Q1 turns off is T2 and the dead time begins. The junction capacitances of the upper and lower switches are charged and discharged at a constant current by the magnetizing current. When C1 charges up to VIN and C2 discharges to 0, this moment is recorded as T3 and this mode ends. You can see the discharge time calculation in the lower right corner. The key is how to determine the value of C1. The formula derivation is not the focus of this video. You can watch the previous modal analysis video. For this equivalent capacitance C1 in the formula, most beginners will directly copy a static COSS from the datasheet table. For example, the 48 picofarads corresponding to 400 volts. Experienced engineers know this is not accurate, so they go and look at the COSS versus VDS curve. Turning to the curve, we can see that the COSS of a MOSFET is highly nonlinear. As the VDS voltage falls from 400 volts to 0, the junction capacitance inside the device can surge by more than 100 times. If you use the static point at 400 volts to calculate the discharge time over the entire dead time, the theoretical value can differ from the actual value by several times. So how do we solve this nonlinearity problem? Change the approach. Find an equivalent linear capacitor whose charge time matches that of the real device. How can they match? As long as it stores the same charge, the charge time will be the same. So how do we determine this equivalent capacitance? First, we calculate the charge stored in the nonlinear capacitor. Q equals C multiplied by V is something we learned when we first studied physics. The total charge is actually just the total area under the COSS curve. Because COSS changes with VDS, a simple multiplication becomes an integral. But this is not difficult either. You can see that here we directly multiply COTR by VDS, that is, Q equals C multiplied by V, and then set that charge equal to the integral we just wrote down. At this point, we have written down an equation. If we divide the overall result of this integral by VDS, we get a COTR. In this way, we turn a nonlinear capacitor into a linear capacitor, which is equivalent to flattening an irregular curve into a rectangle. Using this COTR in the dead time formula gives the theoretical lower limit of time that truly allows the half-bridge node to complete its charge-discharge. Because this COTR contains all the nonlinearity information of COSS, it is more accurate than the information of COSS at the single static point of 400 volts. Coming back to the datasheet, the development board I have here uses NCE transistors. When I turned to the table, COTR was indeed there. But can you guess at what voltage it was measured? 480 volts? Those of us who work on LLC converters all know that the PFC front-end output is generally a 400-volt bus, which is the most common operating condition. Did the manufacturer ever think from an engineer's perspective about what operating condition the device would actually be used in? Now look at Infineon next door. On the same page of the table, they cleanly specify the COTR at 400 volts, which matches your actual operating condition perfectly. I say to the product manager of that manufacturer, listing COTR is a good thing, but can you benchmark the operating conditions against those of your competitors? Most manufacturers are even more extreme. They act as if they have never heard of COTR and do not list it at all. In the end, you still have to look at that COSS versus VDS curve. Let me also remind you here, if your LLC converter has a wide input voltage range, the COTR value integrated under different VIN conditions also changes dynamically. As for the fine-grained calculation over this wide range, we will handle it next episode together with a Python script. So next time you are in an interview and someone asks, "Have you heard of the time-related output capacitance?" Of course I know it. Go and watch Chenxuan's video yourself. Talk is cheap. Let us go directly into PLECS and do a comparative simulation. Fix the dead time at 450 nanoseconds. On the left, use the static COSS. On the right, use COTR. Look at the left side first. In the simulation, we directly use the static COSS from the datasheet table. At 400 volts, it is only 42 picofarads, and the discharge finishes in just 14.7 nanoseconds. If you trust this result, you might confidently leave only a few tens of nanoseconds of dead time. Now let us switch to COTR. The dead time is unchanged. Here we substitute a COTR of 200 picofarad, and the discharge takes a full 70 nanoseconds, more than 4 times longer than the left side. Then we also did actual measurements on the LLC development board, and the measured value was 127 nanoseconds. This is an engineering detail we must pay attention to. That is to say, besides COTR, the junction capacitance in this circuit also include the junction capacitance of the secondary rectifier diodes and the parasitic capacitance of the transformer, and all of these cause the VSW node discharge time to become longer. In the next episode, we will teach you how to handle a more practical problem. Many MOSFET datasheets do not have a COTR parameter at all, and you have to extract a COTR yourself from the curves. We have written a small program to solve this problem. Please stay tuned for the next episode and give us a like.